Recording in progress.
Ja, willkommen zu der diesjährigen Jahrestagung der Deutschen Gesellschaft für Fettwissenschaften. Wir haben ja gerade schon die Mitgliederversammlung abgehalten und ich darf Sie jetzt nochmal alle zusätzlich ganz herzlich willkommen heißen zu unserem tatsächlich sogar zweiten Präsenzmeeting in diesem Jahr, und ich bin also ganz stolz, dass wir das jetzt wirklich geschafft haben und dass wir wirklich auch dann in diesem großen Raum mit genügend Abständen, aber dennoch ein ganz schönes Publikum hier zusammengekommen ist, und ich wünsche uns und Ihnen allen hier viel Spaß bei unserem Programm. Und ich habe als erstes die Ehre, einige Preisträger vorzustellen, und dafür würde ich auf Englisch wechseln. I would like to switch to English to introduce the first awardee in a series of a couple of awardees we have today, because we are somehow in delay in that the 2020 awards, there was no chance to hand those over, and I would like to start with Miss Natalia Castejón. Please come to me on stage. She is the Kaufman Awardee for 2020. And I have to put on my glasses for that. Maybe you just stand over a little bit far away so that we can make a photo. If I would like to read it in German first, but I will translate it. Yeah? Für ihre wissenschaftlichen Arbeiten über die Nutzung von Pflanzen und Mikroalgen zur Gewinnung von Omega-3-Ölen wurde Frau Natalia Castejón aus Angers, Frankreich, der HP Kaufmann-Preis des Jahres 2020 zuerkannt. Die Gesellschaft würdigt damit die herausragende Leistung einer jungen Fachkollegin und wünscht ihr weiterhin viel Erfolg. Leipzig, 18. November 2021. So that means for your scientific works in regarding of omega-3 containing microalgae and plants, you are awarded the HP Kaufmann-Preis of the year 2020, and we would like to acknowledge your tremendous success, and would like to wish you all success for the future. So this is, I can hand over at first. Please. Making some smile. And there is also a medal in silver. This is a portrait of HP Kaufmann, and this is also awarded to you. And for your third hand, we have also some price check, which is in fact just a paper, but you will get some amount of money for this prize.
Also nice.
And I wish you all the success for your future work.
Yeah.
And I'm looking forward to hear your presentation now.
Thank you so much. Okay, so thank you so much for the nice introduction, of course, for the prize. huge pleasure to be here today. And I'm pretty sure that this prize will be a nice push for my scientific career. So thank you again for today's scientific committee. So let's move to my presentation. So today I would like to talk about new sources of omega-3 oils to produce healthy lipids using green extraction technologies and enzymatic modification. So I would like to divide my presentation in 3 parts. It's already on? Yeah, okay. So I would like to divide my presentation in 3 different parts. So in the first part, I will talk about the omega-3 lipid extraction from novel sources. Then I will talk about the enzymatic production of healthy lipids with omega-3 fatty acids. And I will briefly talk about the microencapsulation of omega-3 lipids. But let's start with a small introduction. Numerous studies have been reporting the beneficial effect of omega-3 fatty acids, for example, in the prevention of cardiovascular disease, or in the core development of the brain during the pregnancy, or even to maintain the normal eye vision. However, Western diets are not only lack in the omega-3 fatty acid, but also rich in the polyunsaturated fatty acid omega-3, omega-6. So for that reason, there is a need to increase the consumption of omega-3 fatty acid. But how? How we are going to do this? We know that the main source of omega-3 fatty acid is fish, but with the current demand of omega-3, we cannot continue to take this source as our principal source because we are coming to overfishing. So that's the reason, because we need novel sources of omega-3 fatty acids, for example, oilseeds, that contain the omega-3 fatty acids, alpha-linolenic acid and the stearidonic acid. These plants, for example, Salvia hispanica, commonly known as chia, or Echium plantagineum, or Camelina sativa. On the other hand, we have microalgae that are the primary producers of DHA and EPA. And the next question is how we are going to extract these omega-3 lipids. So advanced extraction techniques, like for example, pressurized liquids, ultrasound-assisted extraction, or microwave-assisted extraction, have several advantages in comparison with the traditional method of lipid extraction. For example, shorter extraction times, less volume of solvent, and decrease of energy consumption. Also, these techniques allows the use of alternative solvents, also called green solvents, like for example, ethanol, ethyl acetate, or even water. So coming to the results, in this work, what we did is to combine the novel extraction technique with green solvents. Like for example, in this slide, we can see the pressurized liquid extraction at different temperature, and we can see the oil yield. So at the highest temperature, we can see that we obtain the similar oil yield in comparison with the Soxhlet method that we did extraction for 8 hours. And also we can see that the green solvents, as for example ethyl acetate and ethanol, also reach a nice oil yield. A similar example we have here with using, in this case, ultrasound-assisted extraction for 15 minutes, and we can see that at 55 degrees, we can achieve a similar oil yield also like the Soxhlet method. So it is known that the advanced technique combined with green solvents, we can have higher extraction yields and also in shorter extraction times. But another work that we did is to extract the omega-3 lipids, but using water and ethanol water mixture. For that reason, we use pressurized liquids with different mixture, for example, 90 to 10, 80 to 20, 70, 30, and 50, 50, and also with pure water. Of course, as expected with the results, we had that with ethanol water, we knew that we are going to get a higher extraction yields. But from the point of view of environmentally, we can see that also with water we can achieve nicer results. And then, after the extraction of the lipids, we analyzed, in this case, the Ecune oil, and we saw that the Ecune oil contained around 50% of the omega-3 fatty acid, and we were able to identify the omega-3 alpha-linolenic acid in around 35%, and the stearidonic acid in around 15%. But we wanted to have a closer look to the omega-3 content and see if these new technologies and also the use of green solvents, even with water, we would like to see if these techniques could affect the omega-3 composition. That's the reason, because here we can see the omega-3 content with the different green solvent that we test. And we can conclude that the omega-3 content of these lipids were similar in percentage regardless the solvent used. And then I would like to talk now about the extraction of lipids from microalgae. And for this, we need to take into consideration that to extract the lipids from algae, we need to first disrupt the rigid cell wall that contains the microalgae. So for that, what we did is to use enzymes to do the disruption of the cell wall and to extract the omega-3 lipids. And then we will combine also with preserved liquid in order to complete the extraction of the omega-3. And in this work, we compare the results with the traditional Folds method that is based on chlorophore and methanol. But another drawback of extracting lipids from microalgae is that microalgae contain also different lipid species. So, for example, for the Nanocropsis caritana, the microalgae Nanocropsis caritana, we were able to identify triglycerols, free fatty acids, diacylglycerols, glycolipids, and also monoacylglycerols. So with this, we come to the idea that maybe it's a good idea to do an extraction and fractionation at the same time of the different omega-3 lipids from the microalgae. So for this work, we combine the preserved liquid extraction with different solvents, for example, hexane or ethanol, and we analyze the different lipid classes. So for example, here we can see the triglycerols, the content of triglycerol, and we can see that depending on the condition that we use, we can reach, for example, we cannot reach a high content of triglycerol using the original microalgae, that means without pretreated enzymatic pretreatment, but using pretreatment with enzymes, we can enrich the triglycerol. At the same way, we did it for the diacylglycerols and also for the monoacylglycerols and the glycolipids. I'm not going to go into details to all of these lipid species, but just to show that with the combination of the enzymes, the preserved liquids, and the different solvents, we can fractionate and extract the omega-3 lipids at the same time. And then I would like to come to my second part of the presentation, that is the enzymatic production of omega-3 lipids using enzymes. So the main objective is to synthesize new lipids with desirable nutritional properties and improve viability for the human body. And the use of lipases have several advantages in comparison with the chemical process of produce novel structural lipids. For example, the use of low temperature, which avoid the oxidation of the omega-3. Enzymes also has a high selectivity and also simple separation and utilization of the reaction products. and then they produce minimal quantity of wastewater, and that's the reason because they are considered a green process. So I would like to show you some of the strategies that I developed during my PhD. So the first one is the enzymatic process to produce omega-3 monoacylglycerol from equiplantagineon using immobilized lipases. Then I will talk about the synthesis of omega-3 ethyl ester concentrate from chia oil catalyzed by the lipases with improved stability. And then I will talk about the enzymatic synthesis of omega-3 structured triglycerol from Camelina oil enriched in EPA and DHA. So let us start with the first one. For this, we first produce our lipase derivatives. So we fix the open form of the lipase in a hydrophobic support in order to have the active form of the lipase. Then we apply these previous lipase derivatives to ethanolysis reaction in order to have the two monoacyl glycerols. And we use a specific lipase in the position 1 and 3 of the triglycerol in order to have our omega-3 fatty acid in the second position of the monoacyl glycerol. And here we can see the reaction kinetics from the enzymatic derivative that we produce and the commercial one. So we can see that for both derivatives, after 1 hour, the triglycerols are completely hydrolyzed, also here. And the theoretical percentage of 2 monoacyl glycerol were achieved. So we can see that the enzymatic derivative that we produce shows similar activity to the commercial derivative in order to produce the 2 monoacyl glycerols. And then, in a further step, what we did was to use the solid phase extraction to isolate our 2 monoacyl glycerol. So we can see the first chromatogram, the original reaction. So we have our ethyl esters and the 2 monoacyl glycerol. And after the solid phase extraction, we achieve a pure fraction of 2 monoacyl glycerol, which we analyze by GCMS in order to see the fatty acid percentage. And if we have a closer look and we compare with the original oil, we can see that we enrich our 2 monoacyl glycerol with the omega-3 stearidonic acid, and the final product contained 25% of the omega-3 stearidonic acid. And in the second strategy that I would like to talk today, we focus on the stability of enzymes. This was a collaboration with Professor Christian Group. And the main objective was to use to produce high enzymes in order to reuse them as many batches as possible. So for that, what we did is to use the pegylation as a strategy to improve the stability of the enzymes. So that the pegylation is the covalent attachment of polyethylene glycol to bioactive substance. And what we did is to cover the enzymes with a film of polyethylene glycol to improve its stability and the redilution for many cycles as possible. So we did the production of our pegylate lipases, and then again we apply them to a ethanolysis reaction, but in this case in order to produce omega-3 ethyl ester from chia oil. And in the slide now, we can see the reutilization percentage and the number of cycles that we were able to use these enzymes. So we compare with the commercial one, and what we can see is our pegylate lipases show a higher stability after the different reutilization cycles. And the commercial one has serious limitation and not even to have the 50% of the reutilization in the second cycle. So we can see that the pegylation of the enzymes is a good strategy to improve the stability of them. And I must say, my last strategy that I would like to talk today is the production of structured triglycerol from Camelina sativa oil enriched in EPA and DHA. We know that EPA and DHA are not present in natural sources of vegetable oils, so that's the reason because we decide to include it in a vegetable oil. So first, for do this, we did two-step enzymatic strategy, and the first one was the synthesis of the 2 monoacid glycerols following the conditions that we developed before. And then we did the transesterification with EPA and DHA ethyl esters using high concentrate of EPA and high concentrate of DHA. So we can see here our results, and in the left side we can see the EPA ethyl esters, and in the right side we can see the DHA ethyl esters. So in general, we can see that the enzymatic transesterification of 2 monoacyl glycerol rendered high production yields, but it was affected also for the type of fatty acid that was esterified. Because we can see that with the EPA, we saw higher production yields than in comparison with the DHA. And I was talking about novel sources of omega-3, how to extract them, or with green technologies, how to modify them using enzymes, but how we are going to incorporate the omega-3 fatty acids into food, right? So for that, we decided to investigate the use of spray dryer to microencapsulate the different omega-3 fatty acids that we produce. So we can see in the slide the microencapsulation efficiency for the lipids, different microencapsulated lipid that we tried. So we saw higher microencapsulation efficiency, almost for all of them around 60%. And the most important thing is that we didn't show a difference in between the original oil and the microencapsulated oil related with the fatty acid composition, and we can see that the omega-3 content before and after the microencapsulation step was similar. And then, just to finalize my presentation, I would like to introduce my new project. I'm currently working at the University of Vienna as a Marie Curie Rewire Fellow. And with my project, Bioalgae, I would like to see if with wing extractions and combination with cascading approaches, we were able to valorize the microalgae biomass. So the main idea is to extract the different compounds, first the omega-3 lipids, then proteins and other minor compounds, until the complete exhaustion of the microalgae biomass, in order to see if we can valorize all the microalgae biomass. And how we are going to do that? The host research group is really an expert in bioactivity evaluation, so we are planning to do different experiments in order to evaluate the bioactivity in cell models. And just to give you some closing remarks, I would like to say that advanced methods are effective techniques to extract omega-3 lipids from novel sources using less volume and shorter extraction times. Also, that green extraction methods have been developed as green alternatives, achieving similar yields to the traditional method, but using green solvents. And then that the study strategies show the potential of novel sources of omega-3 for the enzymatic production of healthy lipids and their promising application in the biotechnology and food industry. And thank you so much for your attention. I will be really happy to answer any questions.
Yeah, thank you very much for this interesting presentation. And are there any questions? Yeah, please. Wait a second. I have to just take over here the microphone.
Thank you very much for the talk. Thomas Seilstecker, TU Dortmund. I have a question concerning the outcome of your extracts when you used ethanol and water mixtures under high temperature.
Yeah.
Do you see, so that was a kind of, I think, slide 7 or so. Do you see any trans-esterification and under these, let's say, rather harsh conditions?
Are we talking about this one, right?
Yeah, for instance.
Yeah, so we also did oxidation studies, and we didn't see any oxidation signals about this.
And trans-esterification?
No, neither. Because I would like to say that, for example, when we are applying the pressurized liquids, we are only doing in 10 minutes.
Okay,
So
the duration, because that was missing here also, is like 10
yes,
minutes.
Yes,
okay.
We applied always 10 minutes for the pressurized liquids.
Okay, and how about the miscibility gap? So how do you retain the oil from the aqueous phase afterwards? Because I assume the oil is not soluble in water.
Yes, so the thing is that when water, we go to a higher temperature, we are in a point of subcritical water, and we change the polarity of the water.
Okay,
right?
Under
so
the extraction conditions, and if you cool it down, you just retain it as an organic phase?
Yes, and after
in
that
we
evaporate the water, and we got the lipids.
Okay, thank you.
First question, Robert.
Yeah, Robert Kurist at TU Graz. Very nice talk. I have a question about the outcome of the enzymatic monoacylglycerol synthesis. So do you observe any acyl migration with that to the other positions? Did you check that?
Yes, we checked that, and I didn't specify it in this talk because I didn't have time to do everything. But we check with different temperatures. So in this reaction, we did it at 25 degrees, and if and let me check. Yes, we did at 25 degrees because if I remember correctly, we check different temperature and we see that the acyl migration rate was higher with higher temperatures. Yeah, thank you.
Thank you for the talk. A question, did you try to use supercritical carbon dioxide?
No, not in this.
Because it is cheaper and it is more green than green.
Yes, you are completely right. Yeah, but we don't have the equipment, so yeah, for sure. It's for sure a good idea to try it also, the supercritical.
Okay, thank you very much for this nice presentation.
Thank you.
And thanks again.